Hi, so here's a simulation for torque. Here we have a wheel. A force is being applied to it, making the wheel rotate. We can see this force in action as the ladybug gains a velocity, shown by the vector. The velocity is tangential to the wheel, which is why it flies off. This wheel is spinning and experiencing accelerated circular motion. This is a direct result of torque. The simulation shows us the velocity and acceleration vectors, and these components of torque, force, and radius, which is also known as moment arm. Torque is a rotational force, represented by F in newtons. We will understand two things by the end of this video. One, the basics of torque and how to determine its direction using the right-hand rule. And two, the components of the torque equation and how to compute the torque of a rotating object. The center of this wheel is considered the pivot point, the axis, and the torque will bring it to a rotation. The radius is the distance from the pivot point to where the force is being applied. So I'm going to set a force at 2 newtons and make the radius 2 meters so that we can see these vectors in play. The blue arrow represents where on the wheel the force is being applied based on the radius I plugged in. As we can see, the acceleration is going to be toward the center and the direction of the velocity is always going to be perpendicular to that vector. Torque is a vector that is perpendicular to radius and force. Its direction is going to be in the same direction of the change of angular velocity it creates, this green arrow. However, typically you would use the right-hand rule to establish the direction. Your fingers point in the direction of the radius and curl in the direction of the force. Your thumb is going to be pointing in the resultant direction of torque. On the worksheet, a number of questions are going to ask you to find this. Your options are going to be to the left, to the right, or towards the paper or away from the paper. Using this technique, you're going to realize there's a three-dimensional aspect to torque. The equation for torque is T, a script T. Radius equals radius times force. Therefore, torque is directly proportional to radius and directly proportional to force. We can see this in the simulation. If we have the wheel at rest experience a force of 0, the ladybug isn't going anywhere because there will be 0 torque on the wheel. If the force is being applied right at the pivot point, you have a radius of 0 and therefore again no torque. In the pre-lab, you're going to have to find the resultant torque given the radius force. I can do one to show the process. Number 3 on the lab says choose a force. I'm going to pick 5 and keep the radius at 3. You get a torque of 15. If I increase the torque to 8 and remain at a radius of 3, I get a torque of 24. This results in a change in which the torque was increased. Just by this use of the simulation, we see that changing one variable directly affects the resultant torque. Looking at the formula, you know you just need to multiply, but we can see that on the simulation as well. If you plug in a force of 6 and a radius of 3, you'll see the value of torque appear as 18 Newton meters. Now this all reveals a directly proportional relationship. If force goes up, so does torque. If the radius is increased, if you apply the force more on the outskirts of this wheel, you will get a higher torque. So establishing a relationship is important. It tells a lot on the conceptual aspects of torque. That's all you need to know. Remember that the right-hand rule is a technique that will help you find the resultant torque, and that torque is a resultant vector of radius and force. Thank you.